Hello and welcome back. In this video we'll look at what we discussed in the last one, which is using certain statistics as estimators for parameters of the entire population. The examples that I'll go through are quite unrealistic for a couple of reasons, which I'll explain. But this is there's a couple of questions on the homework that are like this, so I want to go through an example. So here we've got a family has children aged 2, 4, and 7, and essentially what we want to do is we want to look at the mean of the children's ages and look at all of the samples, and we'll look at the sample means and the actual mean of the entire population, and we'll see that we can use the sample means to estimate the population mean. The reason this is unrealistic is there's only 3 children, and conducting statistics using samples, we normally want samples that are pretty big. 30 is normally a good number for a required sample size. So here we can't get a sample of size 30. So we'll just do what we can with these numbers because it'll be easier to work with. So the first thing that they want us to do is to list all samples of size 2, and we're sampling with replacement. So before we do anything else, let's just list all of the samples. And we're sampling with replacement, meaning that we'll grab an age, put it back, and then grab a second one. This is to make sure that things are independent. If you sample without replacement, if you pick 2 and you don't put it back, then we know that we can either get a 4 or a 7 for the second number in our sample. So that's not independent of your first choice. So we do want with replacement to guarantee independence. So what sorts of samples could we choose? Well, we could choose the 2 on the first for the first number in the sample, and then we'll put it back. And then the second number we could also pick a 2, or if we pick a 2 first, we could get a 4, or if we picked a 2 first, we might get a 7. So next, we could consider all the samples where we pick 4 first. So if we pick 4 first, we might pick 2 second. If we picked 4 first, we might pick 4 again. Or if we pick 4 first, we might get 7. And then the last ones would be if we chose 7 first, then we might pick 2 second, or 4 second, or 7 again. Okay, so these are all 9 samples. The next order of business is to calculate the sample mean of every sample. Okay? And again, with only 2 numbers, it's pretty easy to come up with the mean. So the mean of 2 and 2 is going to be 2. The mean of 2 and 4 is going to be 3. The mean of 2 and 7, so 2 plus 7 is 9, divided by 2 is 4.5. So here are the mean. Here's the mean for each sample. The mean of 4 and 2, 4 plus 2 is 6, divided by 2, because there's 2 elements in the sample, is 3. The mean of 4 and 4 is 4. The mean of 4 and 7 is 11 divided by 2, so that's 5.5. The mean of 7 and 2, well, we already did that. That's 4.5. The mean of 7 and 4, 5.5. The mean of 7 and 7 is 7. Okay, so we found the sample mean of all 9 potential samples of size 2. And now we want to find the mean of all of the sample means. So our sample means are things like 2, 3, 4.5, 4, 5.5, and 7. And we want to find the mean of each one of these. And there are several ways to do this, so I want to follow how the homework does this. So for our sample mean, we're going to find the relative frequency of each one, or the probability that if we were to randomly choose a sample mean, we would choose that sample. We'd use that sample mean. So for instance, 2 is a sample mean, and 2 occurs 1 time out of all 9. So the probability that we would get a sample mean of 2 is 1 in 9. Likewise, 3 happened twice. So 2 out of the 9 times, we could see a 3. 4 happened once, so 1 out of the 9 times. If I would just look for 4.5 is a sample mean, and that occurs twice. 5.5 is a sample mean, that also occurs twice. And 7 is a sample mean, and that one only occurs once. So again, 7 only occurs once, 5.5 occurs twice, and in order to calculate the mean of all the sample means, we're going to take each one of these values and we're going to take it times the probability. So this is going to be 2 times its probability plus 3 times its probability plus all the way down to the last one times its probability. Again, the mean of a discrete distribution like this is going to be the sum of each value times its probability. And if we do this all correctly, we should get 13 thirds, which is the same as 4 1/3, so 4.33. So this is just a calculation that we'd have to do by hand or using a calculator, and this is what we come up with. So now, what we want to do is we want to see, is that a good estimate for the population mean? So we found the mean of all the sample means to be 4.3, 4 1/3. But is that close to the population mean, the mean of everything in the population? Well, the population mean, well, the average, this is mu, the average is going to be 2 plus 4 plus 7 divided by 3. Well, that's just 13 thirds, which is the same. So the mean of the sample means is exactly the same as the population mean. So what this indicates, at least in this example, which is true in general, but we'll just say, based on our example, the sample mean is an unbiased estimator of the population mean, because the sample mean, the mean of all the sample means, is the same as the population mean. So sample mean is an unbiased estimator. Cool. And let's try the same thing for the ranges of the ages. And what we'll see is that the range is not an unbiased estimator. So again, if we write down all of our samples, sampling with replacement, we'll get 9 different samples. And then we'll just go through and calculate the range in each sample. So the range of values is the difference between the highest and lowest value. That's a pretty small range. It's just there's a difference of 0 between them. Whereas here, the difference is going to be 2, and here the difference is going to be 5. The difference here is going to be 2. The difference between the highest and lowest value here is 0. Here's 3. Here it's 5. Here it's 3. And here it's 0. So again, these are all the ranges for all of the different samples. So let's make our little graph. So we've got the ranges, and then the probability that if you picked one of the ranges at random, what the probability that you get that particular range. So 0 is a potential range, and it happens 3 out of the 9 times. 2 is a range, and that happens 2 out of the 9 times. 3 is a range, that happens 2 out of 9 times. And 5, and that happens 2 out of the 9 times. So again, the mean of all the sample ranges is going to be 0 times 3 nights plus 2 times 2 nights plus 3 times 2 nights plus 5 times 2 nights. And then if we add this all up, this is 4 nights, 6 nights, and 10 nights. So that's going to be 20 nights, which is going to be the same thing as 2 and 2 nights. So 2.2 repeating. And right away we can see that's a pretty small range. If we think about the range between the actual values, so again, the actual values were 2, 4, and 7, the range, the difference between the biggest and smallest one, is going to be 5. So the actual range of the population is going to be 7 minus 2, which is 5. And these guys are not equal to one another. So the sample range is a biased estimator. And in fact, I would even go so far as calling the sample range, I wouldn't use it to estimate. I wouldn't even use it to estimate the range of the population. Again, the population, the range in the population is the difference between the most extreme values. Well, what's the likelihood that your sample contains both the highest value and the lowest value in the entire population? That's pretty unlikely. So most of the time, the range is going to be a lot smaller. So in essence, the sample range is usually smaller than the range of the entire population. For unbiased estimators, such as the sample mean, the sample variance, and sample proportions, in these cases, the mean of your sample statistics is going to be equal to the population parameter.